So now we're just going to be doing integration of e. So derivative is pretty easy. Derivative is e to the f of x times f prime. So now we're going to turn it around and do integration, doing it backwards. All right. So right now, the way to do integration is to do a u substitution. And since we know when we take the derivative, we always chain on the derivative of our exponent, then that means when you integrate e, you should always let your u substitution be whatever the exponent is. So our u is going to be 3x plus 1. Always let your exponent of your e be your u. So then you take your derivative, so du equals 3 dx, and then we solve for dx by dividing by 3. So du over 3. So now we're ready to trade out. So this is going to be e to the u, because in place of 3x plus 1, we're going to put a u. And in place of dx, we're putting du over 3. And then I always tell you to put your fraction first. So it's a 1/3 since the 3 is in the denominator. Then you put your function, e to the u, and then you put your du. So now integrating. So when you integrate, you keep your fraction, 1/3. E to the u, in terms of u, e to the u is its own antiderivative. So that's going to be e to the u plus c. And so now you stick your u back in. So this is 1/3 e to the 3x plus 1, and then plus c. So there's my antiderivative. All right, it's that simple. It's just a u substitution. And you always make your u be whatever your exponent is in the problem. All right? So the antiderivative is 1/3 e to the 3x plus 1 plus c. Now remember, these you should never get wrong, because you should always be checking your answer by doing the derivative of your answer to get the original problem back. So don't ever get integration incorrect. There's no reason to be getting those wrong. All right, next one. Again, I'm going to do u is going to be my exponent of my e, so that'll be negative x squared. So du is going to equal, the derivative of this is negative 2x, and then my bookend dx. Solve for dx, so divide by negative 2x. So now I'm ready to trade out. So this is 5x, hang on to that. That'll be e to the u, because I made my u the negative x squared. In place of dx, I'm going to put this fraction, du over negative 2x. So now you will notice the x's cancel away. So the only fraction I have negative 5/2 is my fraction. The x's are gone, and I'm left with e to the u du. All right? So now I'm ready to do my antiderivative. When you do your antiderivative, you keep your fraction. So negative 5/2. The antiderivative of e to the u is e to the u plus c. So then you stick the u back in. So we replace negative x squared. So negative 5/2 e to the negative x squared plus c, and that is my answer. So u substitution, always let your exponent be your u for your e, and just do the standard procedures for u substitution and do the antiderivative. Remember, take the derivative of your answer to make sure it's right. All right, so then this one, my u is going to be, so my u is going to be 1 over x. And I need to rewrite that as x to the negative 1 to make my derivative easier to do, because you're just bringing your x upstairs. So my du is going to equal, do the derivative of this, be negative 1 x to the negative 2 dx, which if I rewrite that is negative 1 over x squared. All right, because x to the negative 2 means take x squared to the denominator. And then to solve for dx, you're basically multiplying x squared or negative x squared over to this side. So it's negative x squared du. So now I'm ready to trade out. This is going to be e to the u, because I'm replacing 1 over x with a u. Keep the x squared in the denominator. And in place of dx, you're putting a negative x squared du. I'm just putting that in parentheses so I don't think that that's subtraction. So that's a negative x squared du. Notice the x squareds cancel. So x squareds cancel. I'm left with a -1 e to the u du. All right. So now I'm ready to do my antiderivative. So when I do my antiderivative, I keep my coefficient. The antiderivative of e to the u in terms of u is still e to the u plus c. And then I put my u back in. So -1 e to the 1 over x is what I'll put in there, plus c. And there's my answer. So -1 e to the 1 over x plus c. And again, if you take the derivative of your answer, you should get this original problem back. All right. Again, use substitution on your e. That's all you do. So u is going to equal e to, to the cosine. So cosine is going to be my u. So du equals, the derivative of cosine is negative sine. And then I put dx. I'm going to solve for dx by dividing du by negative sine. And now I'm ready to trade out. So sine, keep that. This will be e to the u because u was my cosine. And in place of dx, I'm putting this fraction, du over negative sine. Notice the signs cancel. So I've got, as my coefficient, I got a -1. And then I have e to the u du. So this is an easy one. So when you do your antiderivative, keep your coefficient. The antiderivative of e to the u in terms of u is e to the u plus c. And then you stick your u back in. So we're -1 e to the cosine plus c. And there's my answer. Again, take the derivative of your answer and you should get the original problem back. Because when you take the derivative of e, all you do is chain on the derivative of your exponent. And the derivative of cosine is negative sine. So the negatives are going to cancel, and then you're going to have a multiplication of a sine, which is that right there. So when I take my derivative of my answer, I should get the original problem back. I know I'm right. Okay? You should never get these wrong. Ever, ever, ever. Number 8. Now let's start doing some limits of integration. And have numbers on here so we get in the area to the x-axis. All right, so for this one, I'm going to let my u be -x because that's my exponent. So du is -1 dx. So dx is going to equal du divided by -1 or just negative du. All right, so now I'm ready to trade out. So this is going to be e to the u. And in place of dx, I'm putting du over -1. And I can change my limits of integration. So these are x numbers up here. So I don't want to use my x values on this expression because now I'm in u's. So if we trade these out, if I put a 1 in here, it's now a -1. If I put a 0 in here, it's still 0. All right, so now let's do our antiderivative. I know it's going to be keep the -1 exponent. The antiderivative of e to the u in terms of u is e to the u. I don't need the plus c because I'm going to do evaluating between 0 and -1. Okay, the 0's on the bottom, -1's on top. So now I'm going to do the fundamental theorem of calculus. So I'm going to put the top number in first. So it'll be -1 e to the -1. And then I'm going to put the bottom number in. So -1 e to the 0. Now we know e to the 0, anything raised to the 0 power here is 1. So this is just 1. So that's going to make this -1. And we're subtracting -1. So that's going to make that a +1. And then over here, e to the -1 means move it to the denominator. So that's going to be -1 over e. So this is my answer. So -1 over e and then +1. That's my answer. And then if you math 9'd it, you can always math 9 and put it in the calculator, right? Math 9. So if you math 9 this and get a decimal answer, then you put this in your calculator and you should get the exact same decimal answer. Okay? So I did a u substitution to do my antiderivative, and then I changed my limits of integration to match my u, to get u values instead of x values. And then I did the fundamental theorem. Okay, now this one, you will notice, because I've always said every time to always make your u substitution your exponent. Well, in this case, the only exponent on our e is an x, and it makes no sense to let u equal x. That makes no sense because that's just trading out your variable, and that doesn't change the problem at all. So in this case, I don't want my u to be my x. What I want to do is, in this case, I want my u here to be my denominator, because if you notice, the derivative of your denominator, which is 1 plus e, the derivative of 1 plus e to the x is e to the x, which is my numerator. So this is a situation where I have derivative over function. Okay? So don't ever let just u equal x. Don't ever do that. All right, because it's not going to get you anywhere. U has to be something more complicated than just x. So I'm going to let u be my denominator. So then that means du equals, derivative of this is e to the x dx. And then I'm solving for dx by dividing by e to the x. So now I'm ready to trade out. So it's e to the x over, this is my u, because 1 plus e to the x is what I let be u. And then in place of dx, I'm putting this fraction, du over e to the x. Notice the e to the x cancel. All right? So the e to the x's cancel. So I have no coefficients because these are gone. All right? So I guess the only coefficient you could think of would be a 1, but I'm not going to write a 1. And then my function is 1 over u. All right? So this is 1 over u du. Okay? So now, what is the antiderivative of 1 over u? Well, that's natural log of the absolute value of u. Remember, 1 over x is ln of x, so 1 over u is going to be natural log of u. And I didn't trade out my my limits of integration yet, so let's go ahead and do that. These were x numbers, right? I don't want x numbers, so I need to do u values. So if I put a 1 in here, this is going to be 1 plus e, so that would be 1 plus e. And if I put a 0 in there, e to the 0 is 1, so 1 plus 1 is 2. All right? So those are my new numbers there, 2 and then 1 plus e. So now that I've got my antiderivative here, I'm going to evaluate that from 2 to 1 plus e. So now I'm going to do the fundamental theorem of calculus. So I'm going to put the top number in first. So that'd be natural log of 1 plus e, and then minus natural log of 2. All right? And so that's my answer. So it's the natural log of 1 plus e, that's a positive number, so I don't need bars, minus natural log of 2. And that's my answer. Can't do any more simplifying of that unless I wanted to, put the natural logs together by making it a fraction. All right? So that's about all the simplifying you can do there. Now again, you can math 9 it, and our answer here should be the same decimal approximation as the math 9 that you would get with the original problem. So don't forget to trade your limits of integration. Don't ever keep the same limits of integration when you change your variable, because that you can't do that. These are x numbers, so I had to change to u values, okay, by substituting them in here to find out what the u value was. All right, and then I did the fundamental theorem. Okay, these last ones are going back to things that we've done a while ago. So I wanted to remind you and refresh your memory over things that we have done in a long time. It says find the extrema and the points of inflection. Okay, it's been ages since we did this. So this is a good time to review this. Okay, so to find your extrema, that would be your max and mins, right? All right, so to do that, I have to find my first derivative. All right, so my first derivative, the derivative of this is going to be product rule. So it's going to be first times the derivative of the second plus the second times the derivative of the first. All right, so there's my derivative. And to simplify this, I'm going to factor out at e to the x. And when you factor out at e to the x, I'm left with x plus 1. All right, now e to the x is always a positive number. So when I'm looking for extrema, remember, this is where you look where your function's undefined and where it equals 0. All right, and then this is where you do your little table. This is just, it's been a while. All right, and we're going to go from negative infinity to positive infinity. Now, where does this equal 0? All right, e to the x is never 0. It's always positive. So x plus 1, that's going to equal 0 when x is negative 1. So that's my only critical number I have, negative 1. And then remember, we're picking a number in each one of these. Okay, so between negative infinity and negative 1, I might pick x is negative 2. And between negative 1 and infinity, I might pick x is 0. And then I'm putting that in my derivative. Okay, e to the x is always a positive number, so I don't have to put it in there. So all I need to do is plug this into the x plus 2, or x plus 1. So when I plug negative 2 in here, negative 2 plus 1 is going to give me a negative answer. So that means my first derivative is less than 0. It's negative. So that means f of x is decreasing. Remember this? So I took my derivative, I looked for undefined and equal to 0, I make my t-chart, and then I pick a number within each interval. I plug them into the derivative to decide if my answer is positive or negative. If my answer is negative on the first derivative, then my function is decreasing. All right, same thing here, put 0 in here, and e to the 0 is 1, so that's positive, and then it's always positive. And then put a 0 in here, 0 plus 1 is also positive. So f prime of x is greater than 0 in this case, so it's positive, which means my function is increasing. So what's that mean is happening at negative 1? Well, if I'm decreasing and then I increase, that means this is a relative min. Is this coming back to you? So I have a relative min at negative 1. So relative min at negative 1, and then if I want to find my y coordinate, I put it into the original problem. All right, this is my original problem. So if I put negative 1 in here, that's going to give me negative 1 e to the negative 1. All right, and that would be my y coordinate. So that's my extrema. All right, so that's my relative extrema. Okay, now the second thing would be, how do you find POIs? Well, POIs are going to be your second derivative, right? So now I need my second derivative to find my POIs. So this is my derivative here, my first derivative. I'm going to use this form of it. All right, so I'm going to do product rule again. So it's going to be first function times the derivative of the second plus second function times the derivative of the first function. So to simplify this, I'm going to take out an e to the x. So when I factor out an e to the x, I'm going to be left with 1 plus x plus 1, which gives me e to the x times x plus 2. So now I'll look where this is undefined and equal to 0, just like I did up here. So that means my critical number is negative 2. So when I do the table for this one, I'm going to go from negative infinity to infinity, and my critical number is negative 2 this time. All right, so now I'm going to pick a number. Say I pick negative 3 for this one, and over here I might pick 0 again. So this is now looking at the second derivative. So how does it compare to 0? I know it's been a while since we've done this. So if we put negative 3 into our second derivative, remember e to the x is always positive, so I don't have to worry about that. So put negative 3 in here, I get a negative answer. So we're less than 0. So that means f of x is concave down. So remember, we're doing second derivative. Second derivative tells you concavity. So if your second derivative is negative, you're concave down. If I put a 0 in here, 0 plus 2 is positive. So my second derivative is greater than 0, I'm positive. So that means f of x is concave up. All right. So now what am I doing? I'm doing a point of inflection, a POI. All right. So my concavity changed. I'm down and then I was up. So this is a POI. So my POI occurs at negative 2. And if I want my y coordinate, remember, you go back to the original problem to find your y coordinate. So I'm going to plug negative 2 in there. So that's going to be negative 2 e to the negative 2. So I have a relative min at negative 1, and then I have a POI at negative 2. All right. So that was finding extrema and my points of inflection using derivatives of e. All right, so now on this next picture, it actually shows you the graph. All right. So there is the graph of the actual shape that I just did. or the function that I just did. So we found at -1, we had a relative min, and then at -2 was your POI, right? So right here at -1, there's my relative min, and then here at -2, there's my POI. So we are concave up here, and then we are concave down to the left. So if you notice, we were concave down, and then we were concave up. And for our relative min, we were decreasing, and then we were increasing. So this is a decreasing function, then it's increasing. So my relative min, and then here at my POI, I'm concave down, then it turns and goes concave up. So that's using your calculus to determine extrema and points of inflection, and then you can always sketch what the picture looks like because you can determine, you know, the concavity, you know if it's increasing or decreasing, you know where your relative mins are, and POIs.